Okay, so the reason we needed those formulas, the sum is k goes from 1 to n of k, which is n times n plus 1 over 2. The sum is k goes from 1 to n of k squared, which is n times n plus 1 times 2n plus 1, all divided by 6. And the sum is k goes from 1 to n of k cubed, which is quantity n times n plus 1 over 2, all squared. The reason we needed those is because we actually need those are called closed formulas for a sum, as k goes from 1 to n, so then I can then take the limit as n goes to infinity. So why are we wanting to do that? We want to find the limiting value of the lower sum approximations to the area of the region R below the graph of y equals 1 minus x squared. So this is way back in section 5.1 when we first brought this up, right? And above the interval 0 to 1 on the x-axis using equal width rectangles whose widths approach 0 and whose number approaches infinity. So in other words, I want to break up 0 to 1 into n intervals and then use the lower sum, so the right endpoint, right, of each interval. Notice the first rectangle will go from 0 to 1 over n, whatever n is, right? So n is a fixed number. 0 to 1 over n. The next one will go from 1 over n to 2 over n. The next one will go from 2 over n to 3 over n. The last one will go out to n over n, which is 1. So how do I find that? Remember, the area of these rectangles, these lower limit rectangles here, is base times height. So the base of each one of these is 1 over n. So here's the base, 1 over n. The height of each one of these is always the right endpoint. So for the first rectangle, when k is 1, the height is f of 1 over n. For the second rectangle, when k equals 2, the height is f of 2 over n. The third rectangle, k is 3, the height is f of 3 over n. So essentially I have this formula here. The sum is k goes from 1 to n of f of k over n times 1 over n. That's height times base of each rectangle for each k as I step through this. So that's how my sigma notation comes into this. Then I want to take the limit as n goes to infinity once I'm able to evaluate this. That's why we needed those formulas before. So I need to be able to evaluate and get rid of the sigma notation. Okay, so let's just work with evaluating this sigma notation. Now 1 over n, there's no k in there, so that's like a constant in terms of this summation, so I can bring that 1 over n out front. Now what is f of k over n? Well, f of x is 1 minus x squared, so I stick k over n in for x, and I get 1 minus k over n quantity squared. So then I have a 1 minus something else. So remember, we can break up these two summations into the sum of 1 minus the sum of k squared over n squared. But n squared, again, is no k in it. So that can just come out in front of this second notation, this second sigma notation, because there's no k in this 1 over n squared, so it's just a constant. Remember, n is a fixed constant. Okay, so again, I'm still simplifying this. I got to get rid of the sigma notations. So what is the sum as k goes from 1 to n of 1? Well, that's 1 plus 1 plus 1 plus 1 n times. So in other words, this sum is just n. So that's 1 over n times n. Then I have 1 over n squared times 1 over n, so that's 1 over n cubed. And then I have the sum of k squared, which, remember, the sum of k squared as k goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. Okay, so what do I end up having here? I have 1 minus, when I write this all out, I have n times n plus 1 over 2n times 2n plus 1 over 6n cubed. And I want to take the limit as n goes to infinity. So I can break this up into two limits. So what I've done at this point is get rid of the sigma notations. Now I can take the limit as n goes to infinity. So 1 over n times n is 1. The limit of a constant is just that constant. It doesn't matter that n is going to infinity because it's the limit of a constant. This guy is a rational function, right? So I have to multiply the numerator and the denominator by the highest power of n that I see. Well, there's an n cubed in the denominator, and if I were to multiply this out, I would have another n cubed. So that's the highest power. So when I did multiply n times 2n, n plus 1 times 2n plus 1, I get 2n cubed plus 3n squared plus n. 6n cubed in the denominator, multiply above and below by 1 over n cubed. I'm left with 2 plus 3 over n plus 1 over n squared divided by 6. And as n goes to infinity, I get 2. This term goes to 0. This term goes to 0. So I get 2 over 6, which is 1/3, and I get 1 minus 1/3, which is 2/3.